Good morning to everybody. I'm Valerio Di Lecce, a PhD student in the Electronics and Telecommunication curriculum, 24th cycle. My tutor is Professor Alessandro Chini. I will start introducing gallium nitride high electron mobility transistors and their main reliability issues. Then I will give an overview of the RF stress tests we carried out on such devices and of the pulsed stress test we carried out. Then I will draw the conclusions and give some indication of about the future work to be carried out in the year 2010. The reasons for the use of gallium nitride over silicon for high power RF operation can be inferred from the physical properties of the two materials. Gallium nitride has a much wider band gap, which leads to higher breakdown voltage and operation temperature. Its higher mobility leads to faster operation and higher currents. And its thermal conductivity, which is much higher, leads to better heat removal. Therefore, gallium nitride is an exceptional candidate for RF high power and high frequency applications. And in fact, GaN amps can provide output power densities 10 to 20 times higher compared to other compound semiconductor devices. However, they still show poor performance stability at high voltages, as you can see from this graph on the right. So we studied silicon nitride passivated gallium nitride high electron mobility transistors grown on a silicon carbide substrate. All devices were all from the same wafer with a gate length of 1/4 micron. We performed a continuous wave load pool measurement at a frequency of 2 gigahertz, either 3 dB intercompression or with an out to backoff of 8 dB. And devices were always matched for maximum power at each bias applied. DC and pulsed measurements were carried out, as well as current DLTS analysis, which revealed the presence of a trap in degraded devices with an activation energy of 0.5 electron volts, which is in accordance with the previous results available in literature. However, contrarily to conventional wisdom, low input power stresses were much more harmful to the device compared to high input power stress. As you can see from this graph, a device stressed in backoff experienced a much worse degradation in terms of saturated output power, DC to RF dispersion, small signal power gain, and gate leakage current. Moreover, a third device stressed initially in backoff, then into compression, showed an alternate trend of the leakage current, which decreases during compression steps. And this clearly tells that two degradation mechanisms are present. They partially compete, and they both concur in degrading the device performance. Now, one mechanism was recognized as a trap-assisted electron tunneling following the generation of defects under the gate, at the drain end of the gate. And it's a rather slow process which dominates in backoff and has been demonstrated in literature, as you can see from this reference here. The second mechanism could be the electron injection over the gate drain axis region, a relatively fast mechanism which decreases the electric field peak at the drain end of the gate and as a consequence reduces the gate current. Now, our hypothesis is that the first mechanism, mechanism 1, is much slower compared to the RF signal. Therefore, the high electric fields instantaneously reached in compression might not last long enough to activate trap generation beneath the gate, but they might be sufficiently long to inject electrons over the gate drain axis region. And pulsed stress carried out at different switching frequency partially confirmed our hypothesis. As you can see here, at lower frequencies, the gate current, the gate leakage current increases, while at higher frequency, it's steady. So in conclusion, we have found that RF degradation of gallium nitride high electron mobility transistors has a dependence on the drive level. At low input power, the gate leakage current increases, whereas it can decrease at high input power. And two concurrent degradation mechanisms have been identified, one slower, the generation of defects under the gate, and one faster, the electron trapping, probably in the silicon nitride. In the future, we will keep investigating the reliability of GaN amps by means of measurements at 10 gigahertz and numerical simulations to investigate the effect of traps and the effect of the geometrical structure of the device on the performance. Here's a list of my publication for the year 2009. My PhD work was under the FIRB 2006 and the PRIN 2007 project. And that concludes my talk. Thank you all very much for your attention.